During this next segment, we will be explaining and demonstrating how we achieve our flow measurements using moving boats on large rivers and acoustic Doppler current profilers known as ADCPs. Typically, the USGS uses discrete flow measurements for multiple purposes. 1. Develop and maintain stage discharge rating relationships for real-time flow reporting. Document the collected sample's flow condition for instantaneous load computations. And 3, it can be used for establishing equal discharge increment, EDI, stations across the channel for isokinetic, flow and depth integrated sediment and water quality sample collection.
We're all in a basic line, even at every stage. That's going to be your sampling point roundabout. We'll do 5 sections. Of course, they're all cluttered when you zoom out that far, but you can see how they kind of fall in a line most of the time.
We use a variation of adjustable rigid mounts to secure our ADCPs on our boats, all of which are custom made from non-magnetic metals like aluminum, so there are no ferrous metals which could interfere with the unit's compass. There are 2 mounts we will show. The Mississippi boat's ADCP mount is operated on the bow.
This is a custom mount we had made in our office. So it's very easy to operate. We've got our external heading sensor mounted right above the unit. And this is where we have our Doppler mount.
The boat you will see in Baton Rouge has an ADCP bracket mounted on the port bow area. The ADCP for the bow mount is mounted alone with a bracket and a fixed pipe which slides on a slightly larger pipe and is securely bolted to the boat's mount. This design has worked well for many years with over several hundred measurements made. During the 2016 major flood on the Mississippi River, our bow-mounted pipe did bend slightly from the force of water from 10 to 11 foot per second flow, but the mount did not fail. Also, we have numerous mounting holes, which allow us to raise or lower the unit. We have experienced the need to lower the ADCP unit further under the water surface to increase the depth of the head due to air entrainment. We highly recommend attaching a secure rope from the boat to the unit itself in case the mount was to fail, as the unit would still be retrievable and not lost. Once the unit is securely mounted and lowered into position, we check the depth of the ADCP head for that offset and input that into the setup screen before each use. This is needed to accurately compensate for the blanking distance and extrapolated computation of flow. This can be read from any type of marks, but we normally use a waterproof survey type tape attached directly on the mounting pipe itself. We utilize the RDI 600 Hz workhorse unit to make our flow measurements in most of our deep, fast-moving waters with high sediment content. Other RDI units can work as well on deep, fast-moving water, like RDI's River Ray, but we've had good success utilizing the 600 workhorse during all of our large river conditions. The GNSS GPS sensors we use to compensate for moving bed forms are the standard Hemisphere A100. There are other newer models available, but we have had no issues using the A100 units. GPS strings can also be obtained from the external heading sensors. We use the Hemisphere V102 external heading sensor. These sensors are highly suggested at sites with very wide channels to compensate for heading errors. Some of our offices have used other models like the V103 or V104, but we like the smaller V102 units. These external heading sensors should be mounted on rigid mounts near or above the ADCP itself. Setup settings can be found in the attachments of this segment or online at www.hemispheregnss.com.
now that we've launched the boat and we've got all of our ADCP hooked up, this boat is actually set up so that we have a very simplified method. Basically, we're running power off of an inverter. It's being charged by the outboard motors. And so we have AC power for our touchscreen computer that we'll be using to make our Doppler measurement. And so here in just a minute, I'm starting Wind River, and we will start to set up the process. So once I start Wind River, we'll walk through each process on how we set that up, our offsets and our calibrations that we go through, and this is how we make our measurements. So this screen is movable. It is a touch screen. It has a solid state computer base, and so we've had very good luck with this computer.
Then we open up Wind River and begin to fill out some of the more important information to set up the measurement. We start by opening up the file, clicking on New Measurement, and then we just enter the station name, our USGS station number, so that when we file this in our system back at the office, it will be marked as this site. We don't normally fill in all of the information here on the site information under the measurement wizard, but some of the more important things that we use, we do fill out. Our measurement number is a sequence number for the next measurement. The field party would be the initials of the people on board. And process by would be the individual who is actually filling this out and doing the measurement. Of course, deployment type would be manned boat. We put the name of our boat here and the location on the stream where we're making actually the transect. And today we're about 2,200 feet upstream of the I-20 interstate bridge. Then after this basic information is filled out, we go to next, of course. And if we have a stage reading, we'll enter that here as a reference for this time frame. Most of the other things here, we're not too worried about filling out. We do enter water temperature as we measure that with an external sensor because the Doppler does use the speed of sound, and so temperature can affect that.
I am now taking our multi-parameter meter to measure the temperature of the water to compare it to the thermistor and the Doppler to make sure we're getting accurate readings. Taking off the guard here. And within this there are several different probes for water quality. We have pH and temperature, conductivity of the water, and dissolved oxygen.
Then we'll go right into our next screen, and we've got a green light on our ADCP. We've got connection there. The serial number here is 6156. Our external GPS is connecting, and also our external heading. Before we measured our depth of head to be at 1.35 feet. And we're going to read our magnetic variation for this location, date and time from our app. We'll be entering that here at 0.88. And because we visited this site so much and we know it so well, we can estimate that the water depth we're going to see today is going to be around 89 to 90 feet deep. We'll put in a little bit more than that to overcompensate. The maximum water speed will be somewhere around 8 or 9, but we're going to put in 11. And of course, keeping our boat speed under our maximum water speed at 10 foot per second. The bottom mode we leave set at auto. It would be mode 5. The water mode we're going to change to mode 1 for this deep river, fast-moving water. And the update is auto. Our top and bottom methods are power fit, and the left and right are triangle. Here's our program. We're just going to go on through and finish this up. And now we're almost ready to start doing some of our other checks. And right now we're just doing the system tests, and then we'll go into the compass cal. So we've got 23 pass and no fail. So all the systems are working good. We're looking at live numbers here. We're going to stop the PC2 and break that. We want to go through all of these checks to make sure the system is set up correctly. We're going to look at our reference, make sure that we've got that changed off of bottom track, because we do expect some moving bed with these velocities and this sand bed that we have here. So let's check that reference. We are on VTG GPS, and that's what we want to use today. Now we can go in and do our compass cal. And so first we'll calibrate the unit. And we will press the space bar on our keyboard to start the calibration. We're getting the boat into position, and we're going to turn in a nice smooth 360-degree circle. We try to do this in a calm area where we don't have a lot of pitch and roll. And so we're doing this right inside one of the tributaries to the Mississippi River, the Yazoo River. And so our boat driver is just slowly turning the boat in a 360-degree turn to check the compass calibration. We do our best to keep that rate at below 5 degrees per second. And so as we're turning, we started around the southeast direction, and we will end back up in that same direction. So as we're returning back around to complete that 360-degree turn, this procedure will then calculate the setting of that compass at this time, and then we are calibrating, so it will evaluate that when we go to the next step. And we see here we have a 2.7 degree difference. So now, since we've calibrated, let's go back and evaluate what we have just done, and we'll repeat the same procedure, turning the boat at a 360-degree slow turn. We ask everyone on the boat to try to be still, and so there's not a lot of moving around on the boat. We want to rotate it in a flat plane at less than 5 degrees a second rate. So we're almost done evaluating. We should see this 2.7 degrees go down considerably. We're looking for this to be under 1. Normally we have good luck with this, and so I fully expect this number to turn out good. Almost done. These checks are important. Even though they take a few minutes, they're very important to make sure that the unit is set up correctly. So we're at 0.2 degrees. We will accept that number. And so at this point, we just close that window out. And we're almost ready to start measuring. So now what we want to do is look at our external heading sensor. And so we'll go up to Acquire. We'll load our program. And we're going to check our external heading sensor offset by starting and recording this as we would a normal transect. And what we do, our distance to shore, since we're going to be going upstream and downstream to do this for several hundred feet, we just put in 99 for shore distance. start and stop, so that will let us know that this is a check and not an actual measurement. And we want to open up the compass calibration tabular so that we can look at the GC minus BC. And so we're going to let this run. We're recording this so we can play this back at the office and review this if we need to. So we're going to let this run for several hundred feet, and we're looking at the number here, GC minus BC. Right now it's 353.7. So that number would be subtracted from 360 degrees to give our offset. So we're still watching the GC minus BC, and that's GPS course minus bottom course. So we're looking for that difference there, which would be subtracted from 360 degrees. So let's go ahead and end this, and we'll just put 99.99 for distance to shore. That tells us that this is not an exact measurement, but this is the external heading calibration recording. And so from our calculations, we're about 5.2, somewhere between 5 and 6 degrees off. So we want to put that into our heading. But now what we're going to do is we're going to reverse that, and we're going to start this again in the opposite direction to check this GC minus BC on the parallel track. So we'll let this run for another few minutes till we accumulate several hundred feet of recording to look at this difference.
All right, I think we can cut it. 355.5.
Okay, we can end this, and we'll put 99.99 again because this is a fictitious measurement. And we can do our calculations here by hand, taking the average of the GC minus BC passes to subtract that from 360 degrees, and we will input that in the external heading sensor offset under the next transect field configuration. We need to stop pinging. Once we have computed that offset, we can go under properties, and right here in the GPS external heading, there's the external heading offset. We check to use the external heading. We're going to back the 0 offset out and put a negative 5.2. And so every measurement following will have a external heading correction of 5.2 degrees. Now that can change, and our mount is a little loose at some times, and so at times we have gone back in and adjusted that ever so slightly. We're looking at those numbers. I think we'll just leave it. So we're good. We have that set as a negative. So that will correct the external heading to read 360 degrees. If we were to go back in now with that correct heading and do another transect, we would see those numbers be very, very close to 360 degrees with no correction needed since we have that offset in place. So now we are ready to start measuring. And so we can begin our discharge collection. Now we can begin recording one of 2 passes that we will make across the river for our flow measurement. And we can load our program now that we've finished all of our initial setup and test. Once we get the program loaded, and we're seeing some live readings here on our Wind River software. we want to go ahead and make sure our boat is in position and start that by making a measurement to the bank with our rangefinder, being sure that we're on the left bank or the right bank, looking downstream for that reference. And after we enter the bank distance there, we can begin our measurement across the river. As you can see here in our required control window at the bottom right, our raw data is recording, ADCP status is pinging, our GPS status is valid, and so is our external heading sensor status is valid as well.
So we've got our bank distance put in, watching our boat speed here. Boat speed is 2, water speed's 3, as long as we stay at or below our boat speed. We should be measuring somewhere around 1 million CFS today. Boat speed 2.9, water speed 3.4, depth 63. Profile looks good. Configure, we want to make sure that we are not on bottom track, we are on VTG, which we find works best on this river. So because of our program and the gauge is situated below the Yazoo River, so we routinely, 14 times a year or more, depending on flood events, we measure the Mississippi River at this section, just below the mouth of the Yazoo. The Yazoo has a drainage area of about 12,000 square miles, and it's strictly agriculture. There are some farmlands included in that basin, but as you can tell, it has a muddy effect to the water. It's high in fines, silt, clay. So to compute the total discharge for our discharge rating and what we publish online on NWS Web, this is where we measure our discharge for that rating. And then we will shift the rating according to the measurements that we make live on the river. We're getting a nice profile here with the estimated distance on the bottom. Boat speed is 5, water speed is 6. Calculated depth is 92 feet. So this is where we started with lower velocities, and then we're picking up some higher velocities. Look like we've got some 7/8s, a few 8s intermingled in there. We're just about on the peak of this small rise, which is right at the flood stage of the Mississippi River at Vicksburg. So as we measure here and compute the discharge for our site, we will go upstream and measure again at our water quality site, which is just upstream of the Yazoo River. We don't want to include the inputs of the nutrients and the agricultural chemicals like the pesticides and other things in that sampling. It's not a well-mixed zone right here, so we want to exclude some of that. So we'll be up to collecting everything north of the input of the Yazoo River.
One of the things you can look at as you're going across for one of these measurements is you can take off the GPS and see how that affects your cross section and actually the measurement, losing track, bottom track there. So this is what it would be like without the satellite reference. Of course, we want to keep that back on VTG, using that for the tracking. Because we normally do always have moving bed at these sites. There have been times where it's been marginal at extreme low flow, but we always use our GPS. A couple other things to look at. You can go under graph. Let's go. Well, this is a graph here that shows the water speed versus the boat speed. So you can see we're doing fairly well, keeping the brown line below the VTG line, track of the vessel speed. We can also see that in the tabular form under the composite tabular on the far right-hand side. And another thing I like to look at, specifically at higher flows, is the backscatter contour. So you can see here as I blow it up where we're the red, the oranges, the yellow colors here, some of the heavier particles, which would represent the sand that is being suspended and creating the dunes as it moves downstream. The lighter blues and darker blues would be the finer particles. So this is an indication of some of the particles that are being transported by the flow here. Over to the left-hand side, that's more of a dense formation we call the Vicksburg Formation. Maybe some sand there, but not as much as we would see on the left-hand side, the right-hand side. But just some interesting things to look at during these measurements. And I think we can fast forward on to the end of this measurement and move on closer to the end. And as you can see now, we are shallowing up, getting ready to end this transect. And as our captain approaches that depth that we're watching, not to go shallower than 12 foot, we'd like to keep it a little outside of that. We'll start to lose ensembles and get below that blanking distance of 12 feet in this mode. Calculated depth here is 16, so we're holding the boat steady, collecting about 10 pings while the boat is fairly steady.
Now we're going to start our second transect. We're on the right bank. We're in positive flow. So we want to go to acquire. We already started our pinging. Start transect. How far?
98.
All right, 98 feet. On the right bank, check.
Check.
So we'll just fast forward this second measurement over to the end, and then we will discuss a little more on how we review our measurements in Wind River and in this other software that we use that's called QRev, which stands for Discharge Review. So we can fast forward on to the other side, and everything here is looking well. Now we're approaching the bank to finish out our second measurement. Looks like we're very close to the total that we saw on the first measurement. So we believe this will end up being a very good measurement. And the velocities are slowing down, and so we have to slow our boat velocity down as well. Sometimes it's very hard to keep the boat speed below the water speed when you get to velocities that are less than 2 foot a second. So now I think we can end this transect when our captain says the boat is static. And then we can input our shore distance for that portion of the measurement. I'm going to change that 60 now to 69 feet to shore, almost in the same place. And so now we have completed both passes. And we can look here, 11,868 cubic feet per second, difference between the two, which is within 1%. And if we go in and look at this a little closer with our external heading, I believe we can adjust that a half a degree or maybe a degree. We may have put that wrong offset heading for the external heading offset. So we'll need to go in and check that number again to be sure that we input the correct degrees offset. So we can go in and look at that now. So we just stop pinging and we can go back and look at that. But in order to look at that under the properties, we'll have to play back those measurements. Just need to click on the PDOs there for transect 4 and transect 5. There's transect 4 and transect 5. Reload those measurements so that we can look at that. Now go in under field playback configurations, DS GPS external heading. Let's change that -5. What? Let's see. And play that back so that it will take. And we'll need to apply the same correction offset to transect 5 under playback configuration. Let's back that out. Let's try 6.0. See if we're even getting close here, and we are. So we're going in the right direction. So we were a little low on our offset. So let's back that out and try 6.4, -6.4 degrees. And then you'll need to play that back so it can apply that correction. And also set that for the other measurement. -6.4, hit OK. And we'll play that measurement back. And there we go. We're 53 CFS difference between the two passes. Standard deviation average of 0. So basically the same discharge across the channel on each pass. So that's what we would call an outstanding measurement. This is another software that we use. It's called QRev. It was developed by David Mueller from the USGS a few years back. And you can input measurements into this checking software. We'll load this measurement. It asks you, do you want to load all the transects or just the check ones? We'll just say yes for saving some time. It takes a few moments for the measurement to load, but the way this works is these tabs across the top you'll see in a moment will light up in different colors and give you just a great visual of how well the measurement followed our USGS procedures and standards. And so you can see here it starts off in the main menu and these tabs you can click on, and so right away you can see that there's a moving bed test in red, which means it's caution. And if you go down to the bottom here under status, you'll see that there was no moving bed test performed. We've got some other cautions in yellow. The temperature range was outside. The pitch of the boat was a little greater than 4 degrees. And some of the other little checks, but all in all, you can go through these and look at the way that this software reviews the measurement. Here's some of the pitch and roll. We may have had some barge traffic that came through while we were measuring those type of things. Bottom track, we know that that's going to give us a yellow, but our GPS was working well because we had moving bed, and so we used our VTG correction. And all the greens mean that the measurement for these points was well. And so this is just a way of that the USGS checks their measurements. We're required for every acoustic measurement to be run through this software, and it gives us just an overall view of how well the measurement was performed, and may point out some things that we're not aware of. And so you can see that immediately. If we click on the extrapolation here, it will give us a nice plot showing how that was applied from top to bottom of the channel, and also the edges, the edge estimates, how well we applied that on each edge. And so it's just an overall final check, and it will at times adjust the total final Q depending on the extrapolation and a few other items. But it's just an overall check that we use, and this software works really well. I would like to discuss how we document overbank flows during our high water events at Vicksburg when the river has overtopped its banks and is flowing over the floodplain where our large boat cannot reach to measure those areas. Usually, we attempt to make our flow measurements in a section where we can see the right and left banks. But in some flooding situations, this may not be possible due to the channel's meanders or geographical floodplain land use. At Vicksburg, during high flow events, this does occur at times as the flow is contained by the bluff hills on the eastern left bank and by the Mississippi River levee system on the western bank. At this location, the western overbank flow begins about 2 miles north of our section and continues downstream for 6 miles, where the water re-enters the main channel. At that point, the overbank flow overtops the left bank further downstream. To attempt to measure all the flow, we begin by making our main channel flow measurement, starting on the bluff line on the eastern bank. We complete that measurement as close to the western tree line as possible. We also make a second measurement using another crew and a smaller boat through a cleared passage along the bridge pathway to the river's levee. For the overbank flow, we use a different ADCP like the RDI River Ray, which has the capability to measure in shallower depths, blanking distance. Of course, with the wooded overbank, the velocities are much less, with the average depths around 10 to 15 feet. These two measurements are conducted at the same time. We then combine the two measurements to achieve an overall flow measurement. From past high flow events at Vicksburg, we have measured between 14,000 and 21,000 cubic feet per second on the floodplain. We combined that with the main channel flow of around 2 million CFS. We have done these types of overbank measurements 3 to 4 times, and they found at Vicksburg the overbank flow compared to the main channel to be insignificant.
sure to check out the next episode where we discuss proper sampler selection, nozzles and collection bags, EDI versus EWI, setting EDI points using ADCP data, monitoring velocities and depths at deployment, computing transit rates, computing sample efficiencies, deploying the D99 and the D96, P6200 point sampler operation, and BM54 bed sediment operation.